Students, welcome you all in today's class on the topic shear stirrups design. Today we will learn what is shear stirrups and how it is provided in a beam. To begin with, the basic of shear stirrups, how it is formed, how it is prepared from a straight rod steel bar. So you can see here in this image that a straight bar has been shown of a particular length which is required for a ring size. So you can see the various colors has been used. So the change of color shows the place where the bending is to be done. So if you see here, after this the first end, that is the green in color, a band is to be required, that is a yellow is the curvature has to be there. So the first band, if you see from this steel bar, then it will be bent like this. So this green, this yellow and this red portion has been given first band of 135 degree and it is bent. The second portion after this is at a 90 degree bend, that is this one, a blue color. The third band after this is a vertical leg, that is red color, this one, and the fourth is this one, that is the blue color, and the last one is the open end, the second end of the steel bar, which was straight initially. So this two end, the first end and the last end of the steel bar, have been projected inside the core of the section, which will be filled with the concrete. So this core will give extra grip to this stirrups, so that it will not open up when there is some type of deflection or torsion in the member during the movements like earthquake movement. So in earthquake resistant structure, in the specific code, this type of guidelines have been given, that the stirrups has to be given proper grip inside the core of the beam. So this bar is extra extended, approximate length of 10 times diameter. So the shape which has been created here, a rectangular shape, is a shape of a stirrup. So the straight bar has been bent in a very specific way to form this type of shape, and this is a ring form which is used in the beam. It is kept in a vertical position. So you can see here in this diagram there are two vertical legs shown by red color. So this two vertical leg shown by red color is the more effective leg of this stirrup, which is going to support, which is going to give shear strength in the beam. So to summarize, you can see here the first bending was by a 135 degree and followed by another 90 degree, another at 90 degree, another 90 degree, and the last was at 135 degree. And by giving this 5 bends, this type of shear strips has been shaped to be used in a beam. Now it is to be used as a vertical, it is to be kept in the beam in a vertical position. So the name given to this stirrup is two-legged vertical shear stirrups. Now why vertical word is more important here? You can see in the next slide that here is a symbolic a beam has been shown, and over this beam a uniformly distributed load, vertical load, has been applied. The beam is supported by two simple supports. So you can see here the load is vertical. Because load is vertical, similarly as per the principle of shear force, you know that the direction of the shear force is also vertical. Now the leg of the shear stirrups, which is vertical, this one and this one, this one and this one, all vertical legs of the shear stirrups will be effective in the direction of the shear force. So that we are discussing in this lecture detail about the vertical shear stirrups, that is specifically two-legged. So this is the two-legged vertical shear stirrups to protect the beam against shear stressage. Now how it is in isolated way, shear strips cannot be used in the beam. So when several shear strips are used at a particular spacing from this center to this center, so now center to center shear strips is important, which we will design later in this lecture. So several shear strips are used at a specific spacing. Now there are 4 corners in the shear strips you see here. The bottom corners are tied with the longitudinal steel bar, that is the main steel bar, and the upper corners are tied with the anchor bars and therefore in every stirrups there are 4 contacts with the longitudinal bar, and all the 4 contacts at the corners are specifically tied up with the binding wire. So all together after tying becomes so specific in shape that the entire set, the structure of the longitudinal bar and the seated stirrups, this in a network form is used inside the beam. So when we see it, how it is used inside the beam, that if this is a beam portion of the beam, now if you, to sew the shear stirrups, it has been sewn outside the beam, but in principle it embedded in the beam. So all around the beam concrete is there. So after casting of the beam, this entire longitudinal bar and shear strips will be embedded inside the concrete in the beam body by the concrete surrounding every bars and stirrups. And after hardening, suppose after 28 days, the strength developed in this beam will be very good from the point of view of flexural strength. It will be very good in tensile also, in a flexure also, and also very good strength in shear also. So this is the shear stress placed inside beam and has been sewn by this type of exhibit. Now shear stresses are more predominant in this case, and it comes because of shear force. So there are different types of shear stresses. In this slide we are going to discuss nominal shear stress, that is denoted by tau v. So if a beam is loaded with a UDL, that is W kilonewton per meter, and its span is L suppose, and the support are simple supports, then the shear force at the support, that is the reaction at the support, is Vu, that is ultimate shear force, equal to WL by 2, and the tau v, that is the nominal shear stress, is calculated from Vu, that is tau v equal to Vu by BD, where B is the width of this beam. You can see this is the width, and D is the overall depth we are saying here, but the small d is here from the top of the beam to the center of the steel bar which is embedded inside it. So that is the small d, effective depth. So the tau v is calculated by Vu, tau v equal to Vu by BD. So this the numerical value we can get. Now another type of shear stress is the design shear strength of concrete, which is the inherent property of the concrete material because of its ingredients, because its way of casting, because its type of cement, because its type of curing. So because of the all construction practices, the RCC material develops its own shear strength, and depending on the grade of the concrete and the percentage of steel which has been used inside the beam, that is PT equal to 100 into AS by BD. AS is the area of a steel in tension, that is the longitudinal steel bar provided at the mid span, you can say, that is the positive steel tension steel. So the percentage of this steel 100 into AS into BD. Corresponding to this percentage PT and the grade of concrete, we can find out the tau C, that is the design shear strength of concrete denoted by tau C from table 19 of IS 456-2000 directly. So from that table you can see the table is here. So this table is, that is table 19, design shear strength of concrete tau C in Newton per millimeter square as per IS 456-2000, given at page 73. Now in this table, the first column is the 100 AS by BD, that is PT in percentage, and other columns are the grade of concretes. So suppose if the PT is 1.00 and the grade is M20 concrete, then we get the tau C value 0.62. Similarly, if any values are there for PT, we can get corresponding value of the tau C in the respective column, that is the grade of concrete. So suppose in case the PT value is not directly available in this table, it comes in between two values, then we can interpolate. So this has been shown here, that interpolation can be done is suppose the P1 percentage having a tau 1 value, P2 percentage having the tau 2 value, and the PT percentage what is required for us is having a tau C value. Then from this similar triangle method, we can interpolate that tau C equal to tau 1 plus under bracket tau 2 minus tau 1 into the difference PT minus P1 and divided by P2 minus P1. So this gives us the value of tau C at any value of PT, irrespective of it is available directly in the table or not, but we can interpolate always, and this way we can get the value of tau C from table 19. Now what is the method of design of shear reinforcement. So as per IS 456-2000 clause 40.3 and 40.4, there are two cases. The first case is tau v is less than tau c. In this case, the minimum shear reinforcement is to be provided, that is as per IS 456-2000 clause number 26.5.1.5, that is at page 47. So a given formula is there. From there we can find out the SB, that is the spacing between the stirrups, that is the minimum area of shear reinforcement, will give us some specific value of spacing. And in another case, if the tau v is more than tau c, you can see here, when the external load gives more nominal shear stress but the design shear in concrete is less, then we have to provide extra shear reinforcement, that is shear reinforcement is to be designed. In this case, as per clause number 40.4, page 72 and 73 of the IS code. So there are two of the cases. Out of these two cases, in every numerical problem there can be any one. So to more clarify this design problem, we have taken one numerical problem, that is the statement is a simply supported beam having 250 mm width and 500 mm effective depth is supported on 5 meter span and subjected to a UDL of 40 kN per meter over entire span. 4 numbers of 20 mm diameter tension bars are provided. Designed for shear reinforcement, use M20 concrete mix and Fe415 steel. So the longitudinal section with detail of reinforcement where tech gamma f, that is the partial safety factor for load, equal to 1.5. So various parameters are given in this numerical, and we have to find out the parameters for the shear reinforcement. Now to start the solution, you see here that we have given span 5 meter, then the width of the beam B is 250 mm, the effective depth D is 500 mm, FCK, the grade of concrete, is 20 Newton per millimeter square, Fy, the steel yield strength, is 415 Newton per millimeter square. If we assume effective cover, that is 50 mm, then we can get the overall depth of the beam capital D equal to 500 plus 50, effective depth plus effective cover, that is 550 mm. With this data we can calculate the load calculation. The self weight of the beam comes 0.25, that is the width in meter, and 0.55, that is the overall depth in meter, multiplied with the density of RCC, that is 25 kN per meter cube, which gives 3.43 kN per meter. We can round it here, say 4.0 kN per meter. Now the service load given is UDL 40 kN per meter. So total service load and dead load comes 40 plus 4, that is 44 kN per meter. So factored load, small w, equal to 1.5 gamma f multiplied by the total load 44 gives 66 kN per meter. With this, now we can visualize it, that the beam is loaded with the service load 40 kN per meter and its span is 5 meter, but the factored load is 66. So Vu equal to WL by 2, that is 66 into 5 by 2, 165 kilonewton. Now with this parameter, we can now calculate the shear stresses. The nominal shear stress tau v, that is Vu upon Bd. Vu is 165 kilonewton multiplied with 10 to the power 3, that is Newton, divided by 250 into 500. So we get tau v equal to 1.32 Newton per millimeter square. Now the given area of steel in tension is 4 bars of 20 mm diameter, that is 1 bar of 20 mm diameter is 314 mm square. So 4 into 314 is 1256 mm square. Now the percentage of this steel is 100 into AS upon BD, that is 100 into 1256 upon 250 into 500, this gives 1.00%. From table 19 and M20 grade of concrete, from IS 456-2000 we get tau c equal to 0.62 Newton per millimeter square directly, because this 1.00 is available in the table, which we have already discussed, that it is there in the table. 1.00 is there, and corresponding to this for M20 it is 0.62. So the tau c comes 0.62. Now from there we see here that tau v is 1.32 Newton per millimeter square and tau c is 0.62. So tau v is more than tau c. According to this condition, shear reinforcement is to be designed as per the clause given in 40.4 at page 72 and 73 of IS 456-2000. So as per this guidelines of the IS code, we need to find out VUS, that is the extra shear force which is not protected in the concrete, that is VUS equal to VU minus tau C into BT. So 165 into 10 to the power 3 minus tau C 0.62 into 250, that is B value, and 500 D value. This comes 87500 Newton. So this value of shear force is to be provided by the shear stirrups. To find the spacing of the shear stirrups, now we can provide two-legged 8 mm diameter vertical shear stirrups of plain steel, that is Fe 250 bar. Generally for shear stirrups we get plain steel bars, and for a better strength we get 8 mm diameter of the shear stirrups bar. So from this two-legged vertical, two-legged vertical, that means two legs are vertical. From here we can find out the area of shear stirrups vertical leg, that is 2 leg multiplied by pi by 4 d square, that is 8 square, that this comes 100.51 millimeter square. So we get area of the stirrups vertical legs. Now spacing of the stirrups, that is SB, this comes from the IS 456 page number we have discussed here, that is from page number 73. This SB comes 0.87 Fy into SB, ASB into D divided by BUS, and putting all the values we get SB equal to 0.87, Fy 250, ASB 100.51, small d 500 by BUS 87,500. So this comes 124.91 millimeter. We can round it, say 125 millimeter. So we have obtained the spacing of the stirrups from the given formula. Now check for maximum spacing. What should be the maximum spacing for this numerical data? We have calculated SB equal to 125 millimeter, that the spacing of the shear stirrup should be 125 millimeter. But as per IS 456, it is given that the shear stirrups SB value should be around 0.75 D, that is 0.75 into 500, which comes 375 millimeter. Now the upper limit of SB cannot be more than 300 millimeter. This is given in the IS code. Now maximum SB as per the criteria of the minimum shear reinforcement, which is always to be there in the beam for any case, that is SB equal to 0.87 Fy into ASB by 0.4 B, and this is the IS clause which is mentioned here. You can see that when the shear reinforcement should be minimum shear reinforcement, then at this clause 26.5.1.5 page 47, this formula is given from which we can find out the SB value for a minimum shear reinforcement case. So from this we can find out that SB minimum shear reinforcement, that is this value is a type of maximum SB, SB equal to 0.87 Fy into ASB by 0.4 B. So this is 0.87 into 250 into 100.51 ASB value by 0.4 into B, that is 250 millimeter. So this gives 218.60 millimeter. Now out of these four values, 125, 375, 300 and 218.6 millimeter, whichever is the smallest, so smallest is 125, so we should provide SB equal to 125 millimeter center to center spacing between the shear stirrups. Now this spacing is to be shown in the reinforcement sketch with full detail. Now this is a cross section of the beam which we have designed. In this cross section the shear stirrups is this one. You can see the open ends. So this is the shear stirrups, that is two-legged 8 mm diameter at the rate 125 mm center to center vertical stirrups. And when this is having the four bars, 20 millimeter bars, that is the main steel bar at the bottom, that is in the tension face, and two anchor bars, that is two numbers 10 millimeter dia anchor bars on the top. Now when we get this longitudinal section, you can see this is the four numbers of 20 bars at this level, and the two numbers of 10 millimeter bar anchor bars at this level, that is the top near the upper face, and this is tension bar near the bottom face. Now these two are tied with the shear stirrups, and the spacing between the two shear stirrups are every two adjacent two shear stirrups are 125 millimeter center to center, which is shown here. So this way, this is the longitudinal section of the beam, including the main steel bar, the anchor bar and the shear stirrups, and this is the cross section of the beam, including again the main steel bar, the anchor bar and the stirrups. The width is 250 millimeter and the overall depth is 550 millimeter. So by this way we can show that what we have designed the series stirrups for the given load, for the given size of the beam and for the given percentage of the tension steel. Corresponding to that, for the M20 grade we got the diameter and the spacing of the shear stirrups, that is the vertical shear stirrups, two-legged 8 mm diameter at 125 mm center. So this way we have designed the shear reinforcement. If we go through again, we have checked the stirrups. Again we should start from the beginning. In this problem we have discussed that what is shear stirrups, how it is prepared from a straight bar. So 5 bands are taken and this is prepared. Then we have sewn it in the beam in a vertical position. It has been tied with the main bar and the anchor bars, always kept vertical shear strips, that is in a vertical position. Why it is a vertical position? Because the shear force is also having a vertical direction. So all the tied up bars with shear strips are kept inside the beam in the embedded form, and with this we have calculated the tau B, that is nominal shear stress. We have calculated the tau C, and from this table 19, and comparing these two we got that tau B is more than tau C, and for this we have designed the shear reinforcement in this beam, and we have designed the spacing of the shear stirrups, and after designing the spacing we have checked for maximum spacing as per IS 456 guidelines, and finally we decided that it should be having a spacing of 125 mm center to center, and finally we draw the sketch of the reinforcement details with the main bars, anchor bars and shear strips. So with this I hope that we have understood the shear stirrups, its design part and its reinforcement sketch. With this, thank you very much. We will see you in the next class.